Hello, and welcome to the second video in the Supervised Learning course. So in the previous video, we introduced what a supervised learning problem actually was, this learning of a mapping between a set of inputs and a set of outputs. What we're going to do in this video is build a shared vocabulary about how to discuss these different types of model and different types of data. So why is it that we need all of these definitions in the first place? The main reason is to develop a shared language so that we can discuss things in a cognizant way between one another. This is not only between you and I, but between all of the different stakeholders that are relevant in a data science project. These range from statisticians, computer scientists, machine learning specialists, and of course the people with the domain expertise in whatever problem it is that we're trying to tackle. Each of these people bring very different backgrounds and very different ways of talking and thinking about these problems. It's important that we have enough overlap in our vocabulary that we can effectively communicate with someone from any of these areas. So let's begin with different types of data and how we might want to refer to those. The first distinction that we might want to make about data is whether they are qualitative or quantitative. And a good rule of thumb to separate between these is to notice that all data are observed in a certain way, but not all data are measured. And it's this measuring property that is unique to quantitative data. Qualities of an object are observed, while specific quantities are measured. So for example, somebody's height or their BMI might be a quantity that we measure. However, their responses in a survey are generally qualitative. For example, a free response answer within a survey. So let's consider qualitative data in a bit more detail. There are several different types of qualitative data that we can consider. The first broad category of these would be nominal, categorical, and binary data. These have a finite or infinite set of possible labels, and the labels, importantly, aren't ordered. It doesn't make sense to say that label A is greater than or equal to label B in some sense. It's just not well defined. The alternative to this is ordinal data, which has this additional structure imposed where the labels do have an ordering. Again, the number of labels could be finite or infinite, but it's this ordered property that is a key feature of ordinal data. An example here might be men's clothing sizes, going from XS to small, medium, large, extra large, and so on. There is a distinct ordering within these. Finally, we might be considering qualitative data that has less structure, and this might have the form of web scraped text, audio clips, video clips, or an entire scraped website. We'll mainly be focusing on the first category here of nominal, categorical, and binary data within this course, though you may see some things here and there to do with ordinal and unstructured data as well. Moving on to quantitative data then, what types of quantitative data can we have? The first is quantitative discrete, which might be something, for example, such as event counts, gene expression, or a test score. The key feature here is that these take integer values. You might have 24 rabbits in a field, you might have a certain number of genes expressed within a genome, or you might score a certain percentage on a test. Alternatively, we might have quantitative data that are continuous, that are defined on a continuum. So these might be, for example, heights, weights, or times. These might be defined on the positive half line, the entire real line, or they might even define intervals within that. The final way in which quantitative data can arise is through the encoding of qualitative data. For example, the coding of 4 different dog breeds as the numbers 1 through 4, or through the summarization of unstructured data, such as free-form text, as a collection of word frequencies. It's not always so obvious what type of data we have. There are lots of different examples that, depending on context, could be discrete or continuous, and several different flavours of each of those. We'll focus on the idea of colour here. Here we could have them encoded as discrete data types, where we have the RGB, the red, green and blue values for that colour, taking values anywhere between 0 and 255. Same with hue, saturation and lightness. This would give us another discrete way of classifying colours. However, the wavelength of a colour is truly continuous, so deep down we do have something that isn't really discrete. However, if we move back to some examples of phone cases or jewellery, then we might have something that is discrete, where you really only have the option of 4 different colours of phone case. How about some other types of data? Can you see how clothes sizes, a satisfaction score, a measured length, or a scraped web page could be considered as either a continuous or a discrete type of data? Have a think about it. So moving on now, we'll think not so much about data, but about different types of model and how we can discuss those. One way of classifying models is based on what they do. Descriptive models focus mainly on the function f itself and try and describe that, whereas predictive modelling focuses mainly on the outcomes, y star. In reality, most models fall somewhere between these two types, where we're actually interested not purely in f or purely in y star, but in some combination between the two. There are additionally some methods that you've already encountered in the ethics course, which augment predictive models in order to provide them with descriptions. So you can have meta models that are descriptive on top of a predictive model. Instead, you might classify a model by what it does, and the broad division here that is typically used in supervised learning are classification versus regression models. The distinction between these is generally that in a classification problem, the values that you're trying to predict are discrete and usually finite, for example, binary or categorical responses. A regression setting has the responses being continuous or discrete and infinite. One example of this might be when we're trying to predict body mass or return on investments. Again, it's very much a grey area between these two different categories because techniques from one can be adapted to be applied in the other setting. Because people come to data science from a variety of backgrounds, they bring with them a variety of different vocabularies. And so it's useful here to just spend a minute to discuss some of the words that different communities use to refer to the same thing. That matrix X of information that is not about the thing that we're trying to predict is referred to in different communities as a set of predictors, a set of features, a set of covariates, or a set of independent variables. Moving from the left-hand side here, which is more terms that are used within computer science, to the right-hand side, which are more terms used within the statistics and applied stats communities. The thing that we are trying to predict gets referred to variously as a target variable, a response, a dependent variable, or an outcome. Again, moving from more computer science-based terminology through to more statistical. And finally, something that we'll go into in a little bit more detail in the next video is the use of training and test data as opposed to the discussion of in and out of sample performance. You can just ignore the final term here. That shouldn't still be on there. So there are all sorts of different combinations of different types of data and different types of model that we can have. In any case, the process of going from a particular algorithm or model class to an instance of that model or algorithm is referred to variously as model fitting, estimating or learning the parameters of that model, and is also referred to as training the model. This process involves the optimization of a particular loss function in order to trade off between the bias in the model and the variance as well. This is a little bit of a spoiler because it's what we're going to come to look at in the next two videos, so I'll take my time here to wrap this video up. So briefly to summarise what we've covered, in this video we've introduced several different types of data and model that you're likely to encounter in your work as a data scientist. We've seen that the distinction between these is often fuzzy and open to interpretation, but we've constructed a minimal data science thesaurus that will allow us to communicate with a range of different stakeholders on our project. In the next video, what we're going to do is formally introduce the idea of a distance and a loss function. We're going to review several common choices of loss function and why you or someone else might want to use them. Thank you very much for your time, and I look forward to seeing you in the next video.